Hi, my name is Nurul Nafiza. In this video, I'll be explaining wave function collapse and superposition in the Copenhagen interpretation of quantum mechanics. Let's start with a brief explanation of quantum mechanics. Here's a question that puzzles physicists. What exactly is light? For a long time, they thought light was a wave. This idea came from experiments like the double slit experiment, where light passing through two slits creates an interference pattern, just like waves do. But later, experiments like the photoelectric effect show that light also can act like a particle. In this effect, light shining on metal knocks out electrons, but only if the light's frequency is high enough. This led to the idea of wave-particle duality, that light and even matter like electrons can behave as both wave and particles. This brings us to superposition in quantum mechanics. A particle can exist in multiple states at once until we measure it. When we observe it, that superposition collapses into one outcome. This is called wave function collapse, and it's central to the Copenhagen interpretation. In the quantum world, our everyday ideas don't always apply. Quantum mechanics helps describe these strange behaviors, starting with Planck's idea that light energy comes in packets, or quanta. In 1935, Erwin Schrödinger proposed a famous thought experiment to illustrate the strange ideas of the Copenhagen interpretation. He imagined a cat placed in a box with a sealed vial of poison that could be released at a random time. To help illustrate this concept of Schrödinger's cat, here's a short clip from Young Sheldon, Season 1, Episode 8, where the idea is explained in a simple, entertaining way.
Dead armadillo. That's 3 for me.
This is a terrible driving game.
Is a roadkill if it's still twitching?
Both alive and dead, just like Schrödinger's cat.
I didn't know he had a cat.
You've heard of Schrödinger?
You sure? It's a kid from Charlie Brown who plays the piano. Lucy's got a crush on him.
Schrödinger's cat is a thought experiment. A cat in a box is exposed to poison and is both alive and dead until it is observed.
So the cat's name is Schrödinger?
No,
Well, what's its name?
its name doesn't matter.
It does if the cat was dead. Otherwise, what are you going to put on his tombstone?
Not likely the cat's getting a tombstone.
It would in a pet cemetery.
Fine, the cat's name is Mittens.
Because he has little white feet?
Sure,
So in this thought experiment, do you think Mittens is dead or alive?
there's no way of saying until you open the box.
Oh, come on.
Optimistically, I would choose to believe he's alive.
Yes.
Oh, thank goodness.
Oh, dead crow. There ain't no doubt about that one.
As you can see, the show highlights how the cat can be thought of as both alive and dead in a superposition until someone opens the box. This captures the essence of the Copenhagen interpretation that observation causes the wave function to collapse into a single reality. Until we open the box and observe what's inside, quantum mechanics says the cat is both alive and dead at the same time, in a superposition of states. It's the act of observation that causes the wave function to collapse, forcing the cat to be either alive or dead. Schrödinger's equations show the state of a system. The collection of all its measurable properties can be described by a wave function, represented by the Greek letter psi. This wave function contains all the information that can be known about the system. The fascinating part is that two wave functions can combine to form a third, even if they seem contradictory. When wave functions combine, the system is in superposition, meaning it exists in multiple states at once. But in 1957, Hugh Everett III proposed a different idea. What if the wave function doesn't collapse at all, but keeps growing? This became known as the many worlds interpretation. When we open the box, the universe split. In one universe, the cat is alive. In another, is dead. The researchers themselves become part of this larger superposition, which is part of the wave function of the entire multiverse. That's the end of my part. Moving on to Nur Zahida for the next section.
Did you see those two individuals? Yeah, Niels Bohr and Werner Heisenberg, the physicists that developed the Copenhagen interpretation. The thing about Copenhagen interpretation is a bit surprising to a lot of people. because it shows that before we measure a tiny particle, it doesn't have a definite state, but it exists in many possible states. Sounds crazy, right? That is called as superposition. So what is superposition? Imagine a spinning coin that's above heads and tails until it lands. The moment we measure it, the particle state resolves into just one specific state. This means, according to Copenhagen, there is no fixed reality for these particles until we actually observe them. Interestingly, this interpretation doesn't explain how this collapse to one state takes place. It only suggests that it's a part of measurement process. Now, this idea of measurement brings up a big question. What exactly a measurement? Is it a scientific instrument, a human looking at it? The Copenhagen interpretation is a bit unclear here, and many physicists debate it. This is often called the measurement problem. Because of these questions, other interpretations have emerged. The famous one is many worlds interpretation from 1957. This idea suggests that instead of collapsing, a particle state allows every possible outcome of a quantum measurement to occur. The universe simply splits into multiple parallel universes for each outcome. So if a particle could be left or right, in one universe it goes left and in another it goes right, there's no collapse, just endless branching. Another important concept often linked with how quantum phenomena behave is decoherence from 1970s. This isn't a full interpretation like Copenhagen or many worlds, but it helps explain why quantum weirdness seems to disappear in our everyday larger world. Decoherence means the loss of quantum coherence such as superposition and interference in the quantum system due to its entanglement with its environment, leading to the spreading of the quantum information into that environment. This process makes the quantum system appear to settle into a definite classical state. So why do these complex ideas about wave functions, superposition, and collapse matter? Because understanding them often through the lens of Copenhagen interpretation is crucial for new technology like quantum computing. In quantum computers, special bits called qubits use superposition. A regular computer bit is either a 0 or a 1. Unlike a qubit, it can be both 0 and 1 at the same time. This allows quantum computers to do incredible calculations that are impossible for regular computers. Hence, understanding these fundamental principles of the quantum world isn't just for physicists anymore. It's crucial for shaping our technological future and building the next generation of computing. That's all from us. Thank you.